Today we're going to start Chapter 9, and Chapter 9 is another opportunity for us to discuss places where we see rational numbers used. That's what this whole class is about. It's all about rational numbers. And this section is talking about rational numbers as they're used in probabilities. And so if I were categorizing all 4 chapters that we do and which one's my favorite, this is my favorite chapter. That doesn't mean that it's going to be yours, and I recognize that, and that's okay. I think the reason that I like this chapter so much is because it has so many really good applications that you see across all sorts of disciplines, which makes it very applicable to our students and to you too, although it may not necessarily be something you ever teach, and I understand that. So keep that in mind as we're moving our way through, that it has some of those kind of nuances to it. Probabilities. So we need to look at some terminology to start with. First, experiment. An experiment is simply an activity whose results can be observed and recorded. So as we're looking at experiments, they may be a game, right? You can observe the results of a game. They may be a student doing their work, right? When you guys get to doing your PPAT, you're going to be doing some kind of an experiment, You're observing a student doing some things, right? So these are experiments. An outcome is each possible result of an experiment, just the things that could have happened or that could happen. A sample space is a set of all possible outcomes for an experiment. And then an event is any subset of a sample space. Okay? Let's see. Yeah, let me make a pause real quick here and give you an example of an experiment and what some of these things would look like. All right, so let's do an experiment as though we're rolling one single die. You've all seen a die before. It's got 6 sides. It has dots on it from numbers 1 to 6. So the experiment, if we were sort of filling this in, and I'll write it in a different color, the experiment would be to roll 1 die. Okay? So the outcomes are just the list of things that could happen. I could get a 1, a 2, a 3, a 4, a 5, or a 6. Those are the outcomes, individual outcomes, right? The sample space is the set, we put sets in curly braces, of all those outcome options. And then an event is the subset, so it's a smaller collection of the sample space. So it might be something like roll and even. Right, and if I were listing those out, that would be that I rolled a 2, 4, or 6. Or it might be something like roll a number, that's the number sign, not a hashtag, less than 2. Well, that's a funny way to describe it. If I had that description, though, that would simply be the number 1. Right, a number less than 2 would be the number 1. So you can give this in terms of a description, and sometimes it is, or in terms of a list of things, depending on how long the list is. That might be a reasonable way to include that. All right, so theorem 9.1 is called the law of large numbers. It's also called Bernoulli's theorem. So this law says that if an experiment is repeated a large number of times, that the probability will approach a fixed number. So your dice is an example. So if you rolled that die enough times, right? If you rolled it enough times, you would have approximately the same number of times that the 1 showed up, as the 2 showed up, as the 3 showed up, as the 4 showed up, as the 5 and the 6. It would be approximately the same, right? And it would be exactly the same if it were enough times. I mean, like hundreds of thousands of millions of, things like that. Like it would be really big for this to work. So that's sometimes also called an experimental probability, right? A theoretical probability as opposed to an experimental probability. What happens theoretically when you roll the die. Probability is calculated like this, though. It's the number of ways that your event can happen, like your event A. That's what's on top. That N of A means number of ways, or the number of outcomes. In event A. And down here, this is the number of total outcomes. So in our example over here that we created, let's call this right here event A. Okay? Rolling a number less than 2. How many ways can I roll a number less than 2? one way. It has to be the number 1. Okay? So if I want to know the probability of rolling a 2, the probability of rolling a number less than 2, there's only one way that can happen. And how many things are in the sample space, or how many different possible outcomes could happen when I roll the die? 6. So the probability of rolling the number 1, or a number less than 2, is 1/6. And that's what would happen if we did it a large number of times. Approximately 1/6 of the times that we rolled the die, we get the number 1. Does that make sense? Okay. Some events are what we call mutually exclusive. These are events that have no elements in common. For example, if I did evens and odds, those are mutually exclusive. You cannot have a number that is both even and odd. But it doesn't have to include everything. Like, if I left that as your only example, you might think that I also mean that it has to cover all possibilities, and it doesn't. Mutually exclusive just means that they don't cross paths. Okay? They may be far extremes. So it is mutually exclusive if I say a number less than 2 and a number bigger than 5. You can't be bigger than 5 and less than 2. Those are mutually exclusive descriptions. There's no number that satisfies both of them. But obviously there are descriptions sometimes that would. So if I said odd numbers and I said numbers less than 2, it's not mutually exclusive anymore, right? Because the number 1 satisfies both category descriptions. Okay, so mutually exclusive means that these sets have nothing in common. The events have nothing in common. This is notation. If you're not super familiar with notation, it's okay. It is earlier in your book. It's in chapter 2. We do it in number theory. It's not a big deal, but it's telling you that the intersection of these events is the empty set. That's that notation that you're seeing. This empty set means has nothing in common. So if I've ever made a comment on your paper that tells you don't put slashes through your ears, was it yours this time? One of my children in my home did it the other day, and I was like, no, you can't do that. This has another meaning in mathematics, a couple of meanings, in fact. But for the purposes of what we're working with, it means it's an empty set. Sometimes in algebra, we use it to mean no solution as well. So we want to make sure not to put our zeros with a slash through, unfortunately. But this symbol that's upside down means intersection. Intersection just means what they have in common. You can think about the intersection of a street, right? It's the parts that the streets have in common. That's their intersection. Okay, let's keep going. Some probability theorems that we're looking at. So if we have an event, A, and S is the sample space, then the probability of that event is between 0 and 1. So you can think of it like the decimal that corresponds to a percent. There's either a 0% up to a 100% chance that anything you describe will happen, right? Like when we anecdotally say something like, I'm 110% sure, we know that's not true, right? You can't be more than 100% sure of something. We use it in a hyperbole. It's an English thing, right? It's not a math thing. We use it in a sense of being an exaggeration. Everything is between 0 and 100%. But whatever that percent is, its decimal form would be between 0 and 1. So if you looked at 94%, that's 0.94. That number is between 0 and 1. So all of our numbers are going to be, or all of our probabilities are going to be numbers between 0 and 1. The probability that an event is equal to the sum of the probabilities of the disjoint outcomes making up the event. It's a very wordy way to say that we could actually count them up individually, or we can count them together as a group. So if I want to consider rolling a 6-sided die, for example, we could talk about the probability of rolling an even. And what I could do is I could say, okay, how many even numbers are there on the die? 3. How many different options are there on the die? 6. And I know we can reduce that, but hold tight for just a second. But we could also say, okay, well, what are the even numbers? Well, they're 2, and they're 4, and they're 6, right? So I could say, well, the probability of a 2 plus the probability of 4 plus the probability of 6, and I could separate them out and consider them sort of individually. If I consider them individually, well, how many 2s are there? 1. Out of how many sides on the die? 6. How many 4s are there? 1. Out of how many sides on the die? 6. And how many 6s are there? 1. Out of how many sides on the die? 6. And what happens when I add these all together? You get 3 out of 6. So this theorem is just telling you you have the ability to consider them individual cases or in a group sense, and you'll get the same outcome either way, okay? And yes, we would reduce that at the end, and we will now. We'll reduce that. This would be the fraction 1/2. We're going to always reduce our fractions just like we've been doing all the way along. Now, if we have events that are mutually exclusive, then the probability of one or the other of them happening is the sum of the probabilities. So this symbol, again, this comes in the same chapter, for the same portion of chapter 2. This symbol is union. It just means you group them up together. Okay, put them in a group together. So if you want the probability of smaller than 2 and bigger than 6, right, those are mutually exclusive, then you could add them up. How many options are there smaller than 2? 1. How many options are there bigger than 6? 1. And you can just add them together and you can move forward with the probabilities. Okay? If things overlap, you can't do that. If I want to know what's the probability of rolling smaller than 2 or an odd, I have to be more careful. I have to actually count the events that that satisfy either one of them, and I don't want to double count the number 1. 9.5 talks about the complement. The complement means things that are not described. Okay? So if you want the probability that something is even, the complement of that would be odd. But if you wanted to do the probability that a number is less than 2, right, the complement of that would be greater than or equal to 2. It's everything that's not in what you described. It's the other pieces. That's what a complement is. This theorem says that when you add the probability of an event and the probability of its complement, you get 1. And there's 3 formulas here, but they're just manipulating where the pieces are. They're adding and subtracting things from different sides of the equation. They're not different formulas. So as we use them, we'll use them interchangeably, but they're not any different from one another. They are not different from one another. Okay, the next list is really just a summary of all the things we've talked about. It's not anything any different. It's got a little bit more terminology in it than we've talked about, but the first one is the probability of the empty set. The empty set is the set that has nothing in it. That probability is 0. Right? So as I look outside today, I say, what is the probability it's going to snow today? That's 0. It's way too hot for that, right? We might be able to talk rain and have talks about conversations that make sense, but we're not talking snow, right? We're not talking snow. It's an impossible event. The probability of the sample space. The probability that something in the sample space happens is 1. It's going to happen, right? The probability that at some point I stop talking today, that's 100%. It is going to happen. It is a certain event, right? I have to. I got to sleep. I don't talk in my sleep as far as I know, so I'm going to stop talking today. And the third one is one we already talked about. All the other probabilities just are going to be between 0 and 1, right? Depending on how likely they are, between 0 and 1. The next 2 talk about what happens when you have mutually exclusive events. So if you have events that are mutually exclusive, right, they have nothing in common, then when you join them together, you can just add the pieces together. But if the events are not mutually exclusive, this is number 5, this one we have not talked about, then the probability of the events have to be added together, and you have to subtract the probability of their intersection. I will show you an example so you can see that work. But what's happened if they're not mutually exclusive is that you've double counted something. Right? So if I counted the number 1 when I counted odds, and I counted the number 1 when I counted numbers less than 2, I double counted the number 1. So I got to subtract it off. And that's what this subtraction feature is happening right here, is I'm subtracting that off the double counting. And then the last one is one of those 3 versions of the complements. So when we have the probability of the complement, it's 1 minus the probability of the event. And we desperately need an example because that's a lot of terminology, wasn't it? It really is. This is a heavy setup one. So I need to go through a little bit just in case you aren't familiar with this example. And I know some of you've taken classes, like if you've taken contemporary math, you're familiar with this because we talk about this in there as well. But I need to talk about a deck of cards, okay? So depending on how familiar with your deck of cards you are, these problems may be a little bit trickier than others. But if you've played card games at all, you're probably going to be like, why is she talking about this? And that's okay. All right? So we're looking at a standard 52 card deck. So write some of these things down if you feel like you're maybe going to not remember all pieces, or if you're less familiar with the deck of cards. There are 52 cards in a standard deck of cards, okay? Half of them are red and half of them are black. So how many are red and how many are black? If there's 52 in the whole deck, how many are red? Thank you. 26, Chesney says, and she's right, 26. There's 26 red and there's 26 black. Okay, everybody good so far? 26 and 26 is 52, okay? Half red, half black. All right, let's just talk about red. The red cards are also split in half. Half of them are diamonds and half of them are hearts, okay? So you've got a red diamond on them or they're a red heart on them, okay? So half of 26 is 13. So there's 13 hearts and there's 13 diamonds. The blacks get split the same way. Half of the blacks are clubs and half of the blacks are spades. Okay, and to be honest, it really doesn't even matter what they look like for the purposes of everything we're going to do. So if you're like, what does a spade look like? It really doesn't matter. But if you want to go find a deck of cards or look at it online, you'll be able to see, okay? So half of them, 13, are spades, half of them are clubs. So we've got 13 hearts, 13 spades, 13 clubs, 13 diamonds. Everybody good so far? Okay, every card's unique. So let's just talk about one suit now. Let's do hearts. Within the hearts, the 13 cards, every one of those 13 cards looks different. It has a different face value, all right? Some of the cards have faces on them, like legitimate faces. They're either kings, queens, or jacks, okay? Some of the cards have an ace on them. That can be thought of as a high card or a low card, depending on a game you're playing. They've got an ace, and it says an A. And then some of the cards have numbers on them. The numbers go from 2 to 10. So you've got 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you've got jack, queen, king, and ace. Okay, pretty good. And you have all those same cards in the hearts, in the spades, in the diamonds, and in the clubs. All right, using that as our reference point, we're going to consider drawing one single card out of the deck. Okay? We're going to decide which of these things are equally likely. Now, it doesn't tell us we actually have to write the probabilities down. But that's the justification. Like, that's the work you're going to show for this to make sense. All right, so how many face cards are there? Well, there's jack, queen, and king. Ace is not considered a face card and is not considered a number card. Let's just make that real clear, okay? Jack, queen, king are the only ones that they actually have faces on them. Like, they have a picture of somebody. And depending on the deck, it might be more interesting. They sometimes actually have like people's faces on them, but sometimes they're images and stuff too, just illustrations. So if we have jack, queen, and king of hearts, of spades, of diamonds, and of clubs, how many face cards do we have? There are 12. So there are 12 face cards. I'm just going to write these in really small underneath. There's 12 face cards. Out of how many cards are in the whole deck? 52. So this is 12 out of 52. I understand that we could reduce that. For the question that we're being asked, we don't need to. That's not the point. So, just restrain yourself. Don't simplify. It'll be okay. Not face cards. Well, if there's 12 face cards and there's 52 cards, how many of them are not face cards? 40. There are 40 cards that are not face cards. Now, if you just subtracted to find that, raise your hand, because that's what I just did. If you subtracted to find that, you used the principle of complements, right? You used this thing down here. You said, well, how many ways is this going to happen? Well, there's the total number. It's 52. That's where my 1 is. That's representing 100%. And there's 12 of them that don't count in this category. So that becomes the 40 that I'm looking for. That's the complements principle. Okay? All right. So is it equally likely that you're going to select a face card or not a face card? No, because these two probabilities are not the same. One's 12 out of 52. The other one's 40 out of 52. So this one is not equally likely. Make sense? It's just a comparison. And that's why I don't need to simplify it, is because I can compare it over 52 just fine. Right? Sure. All right, how about clubs? I just went through this. How many clubs are there? 13 out of 52. How many diamonds are there? 13 out of 52. How many hearts are there? 13 out of 52. How many spades are there? 13 out of 52. Are these individually events equally likely? Yes, they are. They are all the same probability. So these are equally, I can't write today, likely. How about black? How many black cards are there? 26. Out of how many total? 52. How many red cards are there? 26 out of 52. Are these equally likely? Yes. Okay, are we getting the hang of it? Okay, the last one has the most in it. How many kings are there? How many? 4. There are 4 kings. There's 1 in each suit, and there's 4 suits. So there's 4 out of 52. How many queens are there? 4 out of 52. How many jacks are there? Out of 52. Aces. And if the question stopped right there, would they be equally likely? Yes, but it does not stop right there, so let's count some things then. The next one says even cards. How many even cards are in a single suit? Let's count them. Just a single suit. 2, 4, 6, 8, 10. There's 5. Are there 5? Did you count 5? 2 up to 10? There's 5 even numbers in each suit, and there are 4 suits. So how many even numbers are there? 20. Does everybody understand where I got 20 from? Okay. So the first thing I did is I counted the cards. The card, like in an appropriate way. Counting cards is actually not something you're supposed to do in a casino, just so you know. It means something different. But we literally counted up the cards. 2, 4, 6, 8, 10. There's 5 cards that have numbers on them, and there's 5 of them that are in hearts, 5 of them that are spades, 5 clubs, and 5 diamonds. That's where my number 20 is coming from. So 20 out of 52. How about odd? Is it 20? It's 16. Why is it 16, Abby?
There's only 4 odd numbers in each.
There's actually only 4 odd numbers. Okay, it's not equally distributed because there's not a 1. That's why. So we have 3, 5, 7, and 9. There's only 4 of them per suit, and there's 4 suits, so there's only 16 out of 52. Okay, cool. Good counting, good counting. So then, are these events equally likely? No. Not only that, but interestingly enough, if we had only considered evens and odds, your gut reaction might have been to think that they would be equally likely, right? In terms of most number sets that we look at, that happens a lot of times, but not in terms of deck of cards. So these all together, of course, then are not equally likely.
I have a question.
Yeah.
But if it was like 26, like the last two of those like 26
Mm-hmm.
out of 52, or like, yeah.
Like the same? They both
Yeah.
said 20 out of 52 or something?
Would that mean they were equal at like the whole set or no?
No. So we need all, these are 6 of them, right? If there are the other 6 of them, we would need all 6 of them to say the same thing. If we had stopped short and we had stopped at the king, queen, jack, ace, those 4 are equally likely. But once you throw in anything else with them that doesn't equal 4 over 52, it wouldn't be equally likely. Yeah. Okay, you ready to try something that's not a card example? Okay, let's do this one. Civ. How many of you are in Civ this semester? Oh, it's about 30%. That's give or take. Okay, so some of you are. So this one is describing a Civ class. A Civ class is composed of 21 men, 34 women. There are 22 education majors, 13 religion majors, 12 science majors, 5 English majors, and 3 math majors. All these numbers are made up. Totally. Just created from nowhere, okay? Assuming no one has a double major, we do need to do that. We need these things to be mutually exclusive for this to work, okay? So that's an important feature that this was describing. If a single student is chosen at random, what is the probability that the student is? And then we've got some questions. The first thing we should probably figure out is how many students are in this particular Civ class.
55.
55. Taryn, how'd you get 55?
I just added the men and the women.
Yeah, that's probably the easier one to add, right? Everything else categorizes into something that's more complicated. If I add the men and the women, I have 55. So there are 55 in this class. Okay, we need to know that to be able to do any of this. All right, so let's find the probability of female. So what is the probability that if we chose one person at random, we would happen to select a female student? Well, how many females are there? 34. And how many students are there? 55. And we do need to reduce if possible. So will this reduce? It doesn't. You might be looking at the number 55, or you might be looking at 34, either one. They both have two factors. 55 divides by 5 and 11, neither of which divide on the top. 34 divides by 2 and 17, neither of which divide the bottom. So we're done, okay? How about science majors? What is it? Yeah, 12 out of 55. Good job, Avery. Is this one reduced? What will they both divide by then? Can you think of anything? Let's go back to our 55. What will 55 divide by? 5 and 11. Will 5 or 11 divide 12? No. So this one is reduced, actually. Reduced is good. It means we're done, right? Sure. Now, this one actually has the word or in it. It says we want an English major or a religion major. How are we going to figure that out? We're just going to add them together. They're mutually exclusive events. I have a probability statement that says I'm allowed to do that. Makes sense that I should be able to add them, so we are going to add them. So how many English first. How many English majors are there? 5. And how many religion are there? 13. So we have 5 plus 13 over my 55. What's 5 plus 13? It is 18 over 55. Is that reduced? Yes, it is. Because again, 55 is my denominator. 5 and 11. It's not going to divide the 18, right? So that's fine. So we're at 18 over 55. How about this one? It says neither a math nor a science major. What's that going to mean?
Everything except for math and science.
Okay, we could add up everything except for math or science. Did anybody else have a different thought?
I added the math and the science and then subtracted it from 55.
And that is the other option. You could add math and science together and then take it away from 55. There's neither one right or wrong. They're just two different ways of doing the same thing. Since I heard Taryn mention the adding them together directly first, let's do that. So not math, not science means I'm going to add, let's see, where did we start? Education, that's 22. We have science is 12. English is 5. Oh, I think I skipped religion, didn't I? And what was the religion one? 13. Okay, these are the ones that are not the math and the science.
Wait.
Did I add something I shouldn't supposed to? Oh, I added science in. Well, that was unfortunate. Let's take those 12 people out. It felt like that was more than I was supposed to have. I thought I was supposed to only have 3. Very good. All right. All over 55 still, right? Okay, what is 22 plus 5 plus 13? 40. 40 over 55. Does that reduce? Yes. What does it divide by? 5. Finally, something's going to reduce. So I want to mention this because several of you are doing this as I do your grading. If you're dividing by 5, it really means you're dividing each piece by 5. When you guys write divide by 5 next to it, that's really not what you're doing. You're not dividing the fraction by 5. You're reducing the fractions top and bottom by 5. So if you see me making marks like this, that's what I'm mirroring to you, is that your notation isn't really what you're doing. So what is 40 divided by 5? It is 8, and 55 divided by 5? 11, and that is in fact reduced. So we're at 8 over 11 there. Okay. So let's take a look at a few questions these kind of questions that are following are showing up in the kind of like the question C stuff on your book, those kinds of questions, application kind or working with students kind. All right, so here we have one. A student claims that if a fair coin is tossed and comes up heads 5 times in a row, then according to the law of large numbers, the probability of tails on the next toss is greater than the probability of heads. What is your reply? There's so many things we could say. Somebody tell me something you want to tell the student. Nobody's going to talk to the student? It's going to be a quiet conversation. Well, anytime a student gives you information, you should probably first try to decide if you agree with them or if you don't agree with them. That's a good place to start. Do you agree with the student's assessment that because it's tossed 5 times in a row and comes up one way, that the next toss is more likely to come up the other way? No, we don't agree with them. I hope you don't. That's not going to be a true statement. And there are several flaws in their reasoning. So can somebody tell me a flaw in their reasoning?
Well, it's just like what, like I'm getting ahead of it's not like probability. I feel like.
Okay, so they seem to be looking at the overall outcome if they were doing a bunch of things, right? Not at an individual outcome. So one of their issues, it's not their only issue, but one of their issues is that they're generalizing across a span of rolls, or in this case, tosses, because it's tossing a coin, but they're describing a single outcome, right? If you have a coin, what is the likelihood that it's going to land on heads? 50% or 0.5 every single time, right? This is why you can see people that have like 6 daughters and no boys. Every single time you have a child, it's 50-50, right? It doesn't matter. If you've had 6 daughters, there is no more chance you're going to have a son on time number 7 than there was on time number 1. It doesn't work like that, right? Each individual outcome is its own case, okay? There's something else that they say that's kind of funny. Did anybody catch it? What's funny about that, Avery?
That's not how it works.
Well, it's not how it works, but there's something about it that's even funnier, I think. It's not a large number, right? 5 is not a large number. It might be in certain circumstances, I suppose, but as a general statement, 5 is not big. Right? That's not a large number. So the first thing we might want to say is, hey, 5 is not a large number, so this theorem wouldn't apply anyway. It doesn't even make sense to talk about it. So number 1, 5 is not large. Now, suppose for a moment they came to you and they said, for 5,000 times I've flipped this coin and it's come up this way. Therefore, now it's more likely to come up this other way afterwards. Well, that's still not true. It really doesn't matter whether that would be 5,000 or 5. However, if they told you this happened 5,000 times, you might start wanting to see the coin, because that's not probably realistic, right? The coin might be an unfair coin. Right? Like if that really did happen. So first of all, 5 is not a large number. So, and then Avery, something that you said I want to kind of bring back to attention is that when you said it doesn't work that way, I think was your phrase, right? This law doesn't work this way. This law talks about the average of things that happen over time, not what happens in a single event. It doesn't talk about a single event. It talks about things that happen over a large span of time, right? The averages of things. So a single event is not affected at least not in terms of coins. There are some cases where it is affected. We'll get to those. But in terms of coins, a single event is not affected by what came before or what's after. So in particular, you're talking about before, so we'll write it that way. What comes before it? It stands alone in terms of its likelihood. Is there an E in likelihood? It doesn't look right, but it didn't look right when I left it out either. Nope, I think it's got to be there. We're going to go with it. If it's wrong, somebody's going to tell me later. Likelihood. Okay, it stands alone. It doesn't matter how many times it's been happening before. This time is its own individual time, right? So Thomas Edison, I think, is the one that I'm remembering. Thomas Edison had thousands of failed inventions before he ever was known for his invention of the light bulb. But all it took was that one invention's success to make him known for it, right? But all those failures in front of it did not necessarily mean that when he got to this one event that it had no chance of success. Maybe he felt like it, but it didn't actually have bearing on that, okay? So this isn't the way this works. Let's try another one. This one's a fun one. The following spinner is spun 100 times. Joe claims that the number 4 will occur most often because it has the greatest area of space on the spinner. What would you tell Joe about his conjecture? And then what is the probability that 4 will occur on any spin? So, The first thing you need to do when you're trying to assess a claim is to decide if you agree or disagree with what's being assessed. Are you more likely to land on 4 than the other numbers? I'm seeing lots of shake heads no. So if you're saying no, you're correct. The answer is no. Can anybody offer of why you thought the answer was no?
The spinner's still like in the middle of all 4 of the numbers. It's still 25% chance.
Okay. So he is right that 4 has the greatest area. Do you agree? 4 is definitely the biggest, piece of that cake or pie or whatever. It's the biggest piece. But the spinner has nothing to do with the area. The spinner has to do with the angles that it's spinning through, right? And all of those angles are equal. In fact, you might know from geometry what they're all equal to. Do you? They're 90 degrees, right? Each one of those angles is a 90-degree angle. And if you don't know it's 90, it doesn't really matter. They're all the same is the point, right? They're all the same. So the first thing we probably want to tell him is that the spinning is unrelated to the area. It's spinning through an angle. And each angle is equal measured. So what's the probability of spinning a 4? It's 1/4 because there's 4 angles, right? There's 1 out of 4 angles. They're all equally likely. So we have a 1/4 probability of landing on the 4, just like landing on the 1, 2, or 3. All right. Last question for today, because this is a really good place for us to stop. What if we change the dynamics? Go ahead, write it down. We're good. We're going to change the dynamics, though, of the question. Instead of spinning a spinner, we're going to throw darts. Okay? If we throw darts at the dartboard instead, it's no longer a spinner, right? We're throwing darts. Would that change your reply to Joe? In other words, is it more likely that if you throw the dart, you're going to land in the space marked 4 than in the space marked 1, 2, or 3? Yes, you are. Why? Because there's more area. And when you're throwing something at it, the angles no longer matter, right? It is the space on there that will be the issue. Okay? So will our answer change to Joe? I hope so. It should be. So yes. Then he's right. Our darts are related, or are landing our darts. Let me say it that way. Landing a dart in area 4 is more likely because there's more area. What's the probability that we would land a dart in region 4? It's not 25%, because then that would be equally likely again. It's not 25% of the area, right? So it looks like it might be close to 75%, but do we know it exactly, Jordan? No. So I think we could definitely look and say region 4 is bigger than the others. Are we comfortable with that? But we should also be a little bit uncomfortable with assigning any kind of value to that for a lot of reasons. There's no dimensions anywhere given here, right? So if we had dimensions, could we find that area? Yeah, we probably could if we had some pieces in there labeled and stuff like that. But we don't have that. So I'm going to say, but we don't know, or we don't have the ability to specify the exact probability with the info given. Does that make sense? All right, it's a good place for us to stop. We will pick up and